Иисус нас слышит, кстати. Иисус нас слышит. You know, there is these political issues which... Yeah. Yeah, you know, Western media is spreading rumors that there are some imminent acts of terrorism to happen in Moscow. So many Western people are actually a little bit anxious. Isushi is also anxious because he read about this in Japanese newspapers, and I think his family also is anxious about this. So he prefers to stay at home, at dormitory.
А ты разослал ссылку на Zoom?
Я всем послал вот...
Этому Шену тоже, да?
Шену, слушай, Шену я не послал, потому что ты его не включил его.
Естественно.
Саша.
Ну, Гош,
Саша, я... извини. Кого я еще не...
Значит, этим софт-планом, как бы, между прочим...
Не-не-не, я забыл просто про... Фу, Саша, извини, я просто тут замотался. Я реально замотался. Напиши Шену тогда. Сейчас пока еще.
Тогда надо ждать.
Окей. Ну мы не все пока будем медленно.
Что медленно? Когда Киев спрашивает. А у меня тоже нет его телефона. Только он мне e-mail может написать.
У меня нет его имейла, или если он был, то как-то.
Ладно, сейчас, подожди. 3 минуты. Во-первых, с замечательным инструкциям они приехали черт знает куда.
Я не давал инструкции, это давал Исуши.
Ну, вот том-то и дело.
По-видимому.
Еле-еле.
Okay, so how did you get to the station?
By bus and then by on foot.
Yeah, because walking from the 119 bus, from this 119 bus to the station is pretty far. You know, this station is rather on the other side of the...
There are a lot of slopes.
Yeah, so you probably passed by the Chinese embassy on your way when you walked from the bus station, from the bus stop, didn't you?
What?
When you walked from the bus stop towards the metro station, did you pass the Chinese embassy?
Chinese embassy.
Yeah, did you?
We should take the metro next time.
Yeah, definitely. So you took this 119 bus,
Yes.
and then you get to what metro station did you get?
We take the bus from nearby the university
And where did you go then?
and to maybe I think it's a railway station.
Ah, so that's pretty far away. So it is a long, yeah, Kievska station. That's pretty far away. So, yeah, that's really a long way to go. So the simplest thing to do, the next time you go, you just take from the university. So suppose this is the university, and here is this. The entrance is here. The entrance, the main entrance, which you use when you get inside. And you live on this side of the university there, right? Then if you just go along the road in this direction for like 5 to 10 minutes, even less.
There is a huge slope.
Sorry?
There is a huge slope.
Yes, slope. There is a slope. You just go along the slope,
Yes.
downhill, and then there is
a park.
a metro station right here. And this metro station if you take the train there, it will take you directly to this station, Smolenskaya.
Okay.
Just very simple. Sorry?
You have to change alphabet.
Do you?
First yellow line. Yeah.
Oh, yeah, that's the yellow line. Sorry, yeah, you have to change. But still, this change is pretty. You're right, Isushi, right. So you have to change once, but that's very simple. Just cross the platform to the other side. Just cross the platform. You just go for 2 stations till Park Pobeda, then you cross the platform to the other side and take the train for 2 more stops, and then you are here. So you just 4 stops, and you are here. Yes, thank you, Sushi. I am sorry for this. I actually rarely go by that, through that. Саша, ну как там подошел этот еще наш один человек?
Я только послал письмо.
Ага.
Я не знаю.
Я просто не знаю, ты ответом пошли мне на письмо, которое я слал. его адрес, чтобы я включил его в следующую рассылку автоматически, хорошо?
Отлично, попробуй. Сейчас. Я не знаю, он вообще как выглядит.
Просто, по-моему, в прошлый раз ты ему пересылал, а не я.
Я пересылал.
И поэтому я не знал даже его адрес, если честно. Okay, we can start just little by little. Okay, I hope next time we shall have more more people in the audience, but okay, in the room. So last time I talked about the deformation theory, the deformation problem, and reduced this problem to the description of Maurer-Cartan elements in the Hochschild, in the differential credit algebra of polydifferential operators. So let me recall this briefly. So suppose you have a smooth manifold M equipped with a bivector pi, which verifies this condition. Then the problem is to find a series of bidifferential operators B equal to the sum of k from 1 to infinity h to the power k bk, where every bk is bidifferential operator. So bidifferential operators, I'll denote them by d poly with 2 here, right, with a superscript 2 of M. Sorry? Там запись я не запускал еще. Да, тут нужно запускать. Я просто на YouTube... Нет, тут и легко. А вот на YouTube я не умею запускать запись.
Ну, на YouTube я пойду.
Хорошо. Окей. Да, если запишу. Я запишу тогда в облако. Я запишу в облако. Угу. Запись в облако. Да, вот так вот.
Recording in progress.
Okay. Okay. So I'm recalling the deformation problem for everyone. Suppose we have a manifold M equipped with a bivector pi verifying this sort of equation. And the problem is to find the formal power series in H bar, where every element bk is a bidifferential operator, and such that the product, the f star g equal to fg plus sum of h, plus, b of fg is associative. I also forgot to say that by definition v1 is assumed to be equal to the bracket, the Poisson bracket induced by pi. And then this equation, this condition, associativity condition, is equivalent to the condition that B verifies the Maurer-Cartan equation. That is delta of B plus 1/2 of the commutator of the Gerstenhaber bracket of B with itself is equal to 0. So here delta is the Hochschild codifferential. And the bracket on the right is the Gerstenhaber bracket. I explained these two notions last time. That's the deformation problem. And in order to explain the relation of this problem with what follows, I need to look at the left side of this problem, so to say. Let us only consider polyvector fields. So let T poly of M dot stand for the space of polyvector fields. On M. And this polyvector fields is again, the space of polyvector fields is again a differential Lie algebra, a graded Lie algebra. With zero differential, with trivial differential. And in this case, the condition 1 can also be interpreted as a Maurer-Cartan equation. Namely, d pi plus pi comma pi is equal to 0. So this term here is missing because the differential is actually equal to 0. So this equation 1 is equivalent to the Maurer-Cartan equation. Yeah, of course, 1/2 is also necessary on pi. We also have a map called the Hochschild-Kosten-Rosenberg map from the polyvector fields of M to the polydifferential operators. That's what I explained last time. So this map consists of taking a polyvector field and reinterpreting it as a polydifferential operator Fp, just by substituting the differentials of the functions f1 through fp as the arguments into this polyvector field. This map commutes with the differential in the sense that the image of this map is always closed polydifferential operator. And in this case, it is equal to, in this sense, it is equal to the Hochschild-Kosten-Rosenberg map applied to the differential applied to P. Because differential is 0 in polyvector fields, right? So we have a cochain map. And if this map intertwined, if it hadn't intertwined, I'm sorry, not quite, I don't feel myself secure with the conjunctive mood in English. So I think if it had intertwined the Lie structure, that is to say, if the Hochschild-Kosten-Rosenberg applied to the commutator, to the Schouten bracket of two polyvector fields, if it were equal, so let me put it in quotation marks here because it is not so. If it had been equal to the Gerstenhaber bracket of the image, I'm omitting this HKR from now on, of chi applied to P and Q, then definitely just applying x chi to pi would be a solution to our problem. Just putting b equal to chi of pi is enough, would have been enough to solve the problem. Unfortunately, this is not so. Unfortunately, this is not so. And let me explain why. in some sense. And the reason is for this is that, well, first of all, chi is not a homomorphism. Of the algebras. It is, in some sense, almost a homomorphism. It's almost an isomorphism, but only in a homotopical sense. That is to say, if you pass from the polydifferential operators to the ecohomology with respect to the Hochschild operator, so then chi would be just an isomorphism of differential of graded Lie algebras. So I'm using the same symbol chi for the map induced in cohomology, but it is a little bit different map. So if you pass to cohomology, then this would be an isomorphism. But that means that the difference of this chi of P and Q minus commutator of chi of P and chi of Q is not 0, but is equal to delta of something. That is called U2 of PQ. Sorry. My phone is calling. I'm sorry. I'm sorry, that was my brother. May I make a little bit break? I need to answer my brother. Дима, я занят сейчас занятие. Что-то срочное? Нет. На понедельник у нее было. Дима, слушай, прекрати. В прошлой неделе я тебя предупреждал, что не смогу прийти из-за того, что Клава была. Все, пока. I'm sorry, it's for some family issues. Okay, let's go on. So there exists such map, a map U2 of PQ, such that differential applied to the value of this map is equal to this difference. So one can try to use this map. This map was first described by, for instance, in Gerstenhaber paper, where he introduces these Gerstenhaber brackets. He has a description of such a map. One can try to use this map to find a correction to get a correction term. In the sense, if you take chi of pi, then of course chi of pi commutated with chi of pi is not equal to 0 in general, because it is not equal to pi of the commutator of pi and pi. However, it is equal to delta of U2 of pi and pi. Right? So you can try to take delta. Sorry? Up to the sign, and it doesn't matter actually. Which, if you prefer these, then it is. It's just kind of sign issue. That's not a big problem actually. So just take chi of pi. So you try to take b equal to chi of pi. Then of course you see this doesn't work. Then you take chi of pi plus u2 of pi and pi. And in order to make this look a bit better than it used to, you add h bar here, right? So that's the first and the second term of your b. b1 plus b2. Right? And then you try to write this Maurer-Cartan equation here. You see that delta of, sorry, what's wrong? Delta of u2 of pi and pi. Well, let's forget about this for a while. So delta of b, what is delta of b? It is equal just to delta of u2, right? Just equal to the delta of u2. But then you also have the bracket of b and b. So what is bracket of b and b? It is bracket of chi of p with chi of p. But also there will be the bracket. So if there were only these two terms, there would be no problem. You see? Because then these two terms will cancel out and you are done. You have your associative product. But then it turns out there will be one more term, which will look like up to the sign and something as the commutator of chi of pi and u2 of pi. So you need also to kill this. So you need to add something to kill this term as well, right? And so if you try to do this further and further, you'll see more or less the same old deformation problem which you used to solve by hand before. But it turns out that if you look at the old algebraic structures which has appeared here, then you have a kind of, you can call it a royal way to solve this problem. So let me try to explain this royal way for you. So to explain this royal way, I need to go a little bit into topology, because topology is the science where this notion of higher homotopy algebras originated. Higher homotopy structures. So why we need them, I try to explain. Let me again explain this. We try to amend the lack of homomorphism for chi by adding this correction term, which is just a homotopy between chi and the commutator of chi of commutator, commutator of chi of pi and chi of commutator, right? And it turned out we need more homotopy to kill some extra terms which appear here, right? So if you try to perform this further, you'll see that you have more and more you look for more and more homotopies to kill more and more terms like that. So the first branch of mathematics which ran into this problem was topology. So I think it is proper time to give a little bit of topology for you here. So in topology, people study various infinite dimensional spaces which are obtained from other spaces by certain functorial constructions. For instance, one of such popular constructions is the loop space. So roughly speaking, loop space of a space X equipped with a point x0 denoted by omega, capital omega of x comma x0, is the space of all maps gamma from the unit segment into X with the only condition, continuous maps of course, with the only condition that the ends of this map, the ends of this curve coincide and coincide with this pointed, with this picked marked point. So this loop space is a pretty nice device and has been studied extensively in topology in the middle of the 20th century. And one of the main ideas which made the use of this loop space so popular and so productive was this loop space bears a natural algebraic structure, or almost algebraic structure. When you have two loops, alpha and beta, of this sort, then you can consider concatenation of these two loops as a map, as a loop, which first travels along alpha with the double speed. And then travels through beta at the same double speed. This is a very nice algebraic structure, only for one reason. It has no algebraic properties. Namely, alpha star beta star gamma is not equal to alpha star beta star gamma. So if you change the order of parentheses here, you obtain different loops. And that's clear because here you have to travel along the loop alpha with a speed 4 times the speed of the usual loop. Then you travel along beta with the same 4 times velocity. And then you travel along gamma with double velocity. But on the right hand side, you have first to travel along alpha with double velocity, and then beta and gamma follow with quadruple velocity. Of course, this discretion, this difference can be easily ruled out by reparametrizing the loops. And this can be done uniformly. So to say, you can map a change of parameter, which I draw like this. This is kind of the way you change the parameter traveling. So this is t, the time along the loops, and this is the time in the opposite direction, in the direction in which you change the parameter. So this reparameterization also goes with time, but in the opposite direction, right? So this, you can reinterpret this picture as giving you a map from omega x. So I will abbreviate this loop space of x, where x0 is understood, just to this symbol. Omega of x times its times to the power 3, to the third Cartesian power, times the unit segment, which is usually denoted by I, 2 omega. So that when you take this parameter to be equal to 0, you obtain this map. And when you take this parameter equal to 1, you obtain this map. So you can regard this map as a kind of homotopy between map of this sort and a map of this sort. Right? Kind of homotopy. So you have 2 maps from here to itself, and have homotopy, right? Great. I'll denote this map. I don't know, I will not even denote it somehow. I just will denote this I as P1. And P0 for me will be just a point. Right? I mean, now we have a map from, okay, this map here from this is a kind of polytope. You also have a map of this sort. So this is just the product, just the concatenation. You have also this. Let's go a little bit further. And consider quadruple product of omega x, quadruple, the fourth Cartesian power of omega. Suppose, that is to say, I'm taking 4 different loops, alpha, beta, gamma, and delta. How many different ways to form a product of these 4 loops I have, assuming that I always have to put parentheses? It turns out there are exactly 5 different ways to do so. First, you can, for instance, do this sort. Right? But then you can, for instance, pull this, sorry to say, these parentheses from alpha beta to beta gamma. And it will give you alpha star, beta star, gamma star, delta. Then you can, sorry. Then you can pull these outer parentheses from alpha star beta star gamma to alpha beta star gamma star delta. Right? Then what you can do further, you can actually pull these parentheses from beta gamma to delta, stay inside the outer larger parentheses, right? So it will give you alpha star beta star gamma star delta. After this, you can take these parentheses and draw them from here to alpha beta. Is it clear? So you regard these as a unique path, and then you just pull the opposite parentheses from here to alpha beta. So this gives you alpha star beta star gamma star delta. All these can be done using this sort of map, you see? Because actually this map allows you move parentheses from any point, from any place to any neighboring place, right? So all these can be done by the map. Let me call this H1. H1, 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 H1. And of course, you can also do the same trick here. You just pull these parentheses from here to here, doing the same thing here. So I also have H1. Look at this picture. You have the boundary of a pentagon, and for every point of this boundary, you have a map from a quadruple product of loop spaces, of loop space, into itself. So you have a map from a quadruple product of loop space parameterized by the boundary of pentagon into the loop space. And you can ask if it is possible to extend this map from the boundary of pentagon to the rest of the pentagon. And the answer is yes, you can actually do this. So let us denote the pentagon by P2. And it turns out we have a map times P2 into omega x. And this map extends to the internal part of the pentagon, the map given by previously known maps on the boundary of the pentagon, right? It turns out that this process can be moved further. Namely, Jim Stashev in 1963 proved the following theorem. First, it consists of two parts. So I'm kind of putting together two different results, but they are in the same paper, more or less. So two theorems. First theorem is that for every, so they exist. Series of polytopes P0, P1, P2, and so on, Pn, such that Pk is Euclidean polytope of dimension k, right? The boundary of Pk can be decomposed into Cartesian products of polytopes of lower dimension. So it's a union of Cartesian products of polytopes, of Pi I less than k. Right? And for every k, there exists a map h omega x to the power k plus 2 times pk into omega x, such that let us call this map x hk. Hk restricted to the boundary of the polytope is given by compositions of previously known maps and concatenation of loops. So, for instance, in case, let me briefly describe the idea of this construction. So, I'm not going to speak about the dimensions 4, 3, 4, and so on. Actually, if you want, you can find this in many textbooks. These polytopes are called associaedrons. Associaedrons. How do you pronounce this? Yeah, associaedrons. I don't know. Okay, and never mind. It's tongue twister. I'm losing miserably. Yeah, I'm failing miserably. So, actually, the vertices of pk are in 1-1 correspondence of all possible ways to put parentheses into the product, an associative product of k elements. Yeah, all possible ways to draw parentheses. All possible placements of parentheses. Of brackets, of parentheses. Right? So it's just like what we had here. Then, how do you extend this map from the boundary into the internal part of pk. For instance, in case of pentagon, you do the following trick. You take the center of this pentagon, and then you put the map. Let me call this alpha star hat, beta star hat, gamma star hat, delta, in which all the paths alpha, beta, gamma, and delta are passed with the same velocity. That is to say, each of them takes only 1/4 of the time to travel. So you put this map here. It is definitely an element in the loop space, right? It is definitely an element here. Now, here, 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 and here, and here, you have certain other paths which differ from the path you used in the center only by reparametrization. So you draw this piecewise linear reparametrization along these radii. And then you extend this reparametrization linearly into these triangles, just along the radii again. And that will give you the map you are looking for. So this idea is pretty simple and straightforward. And this idea can be extended further to any dimension with a little work, actually. I mean, for any pk. For any dimension, but k is dimension.
It's just like a partition of 1 to some
It's not partition of unity, definitely. It's not, but it's kind of, I'd rather say it's kind of simplicial maps. That's something like that. You can extend a simplicial map from boundary inside just by linearity. You see, when you have a simplicial map on the boundary, then you can actually use this convex structure on the simplex just to extend it further inside the map, inside the simplex. More or less, this is the idea, more or less.
So any point in this pentagon can be
Yeah.
determined by the velocity of each.
Yeah, definitely.
Yes, and maybe each of them is more than maybe if you have how many? If you have 5 of them, each of them is.
And then you have to go into dimension 3. If you have 5, yeah, if you have 5, how do you call this? 5 paths, 5 loops, you have to go into dimension 3. Then you have a convex body in 3-dimensional Euclidean space, which is called a sociohedron. And yeah, there are lots of pictures. You can find this in Google or in Wikipedia if you just type if you just Google sociohedrons, you'll see lots of pictures. But the idea is pretty simple and pretty straightforward here, right? But what is more interesting is that Stashev managed to prove the opposite statement, which I think I'll formulate here for the sake of completeness, although I'm not going to give any idea how this can be proved because it's purely topological construction. So the opposite is the following. A map, a space Y equipped. I'm being a little bit rough. Equipped with non-associative. With a non-associative, but homotopy associative. But homotopy associative product y plus y into y is homotopy equivalent to omega x for some x, such that the product can be identified. The products are identified. The products. If and only if there exist maps hk from y to the power k plus 2 cross pk into y, verifying all these conditions. Verifying all these conditions as on the left, as in 1. So this opposite statement is a little bit tricky, because here you have to produce this homotopy identity, homotopy equivalence. You have to produce this space X and its loop space, and there are lots of, so there are some topological tricks you have to do, like you have to replace certain maps by their vibrations and so on and so forth. But I'm not going to go into the details. I don't know the details myself, so I just admit this. But that's more or less standard thing from topology, standard fact from topology. Now, as you see, this structure encodes the product in loops. The homotopy of this product in one order and in the other order. Homotopy between homotopies, and so on and so forth. So this structure is actually the first known example of higher homotopy algebraic structure, but in topological setting. This structure is called A infinity structure. The space which bears the structure is called A infinity space. In order to go from homotopy, from topology to algebra, we are now going to go from topology to algebra. To this end, there are lots of different ways to do this. To this end, one can, for instance, replace every space in question by its chain or cochain complex, and then use various functorial properties of cochain and chain complexes to replace the maps by chain and cochain maps between these chain and cochain complexes, right? I'm not going to do this, but roughly speaking, if you just try to do this a little bit, try to think about this a little bit. If you replace omega of x or y by their chain complex or cochain complex, let's call it V, then the map, probably chain complex is better. The chain complex, then the map from omega from y to the power k plus 2 cross p k into y is just the same as map from v to the power k plus 2 times the chain complex of this polytope. Into V, right? But the chain complex of polytope is pretty simple. It has one top-dimensional cell, right? It has only one top-dimensional cell. So we just take this top-dimensional cell, which is actually the only thing new. All the other elements on the boundary, they are known from before, right? We know them from earlier times. So we just take this top dimensional cell here. So this cell has dimension k. Then, of course, when you take the tensor product of V tensor k plus 2 by just ek, we can actually remove this. It is one-dimensional space, right? So linearly, there is no difference between this tensor product and tensor product with this top dimensional cell. But on the right hand side, we shall have to make a shift of dimensions, because this cell has dimension k. So on the right we have to shift the dimension by k, right? You see? So if you elaborate this a little bit, you'll get the following definition, purely algebraic definition of A infinity algebras, or what they sometimes, how they sometimes call this. You get the definition of strong homotopy associative algebras. Definition. A vector space, a graded vector space, graded vector space V is said to bear the structure of a strong homotopy associative algebra, or A infinity algebra for short. Is an A infinity algebra. So now I'm just changing the perspective of my view just a little bit. Here I spoke about chain complex, but it is more convenient to speak about cochain complex. The difference is that in chain complex, the differential changes the dimension by -1. In cochain complex, it raises dimension by 1. However, one inconvenience, one difficulty with cochain complexes is that if you use cochain complexes here, you have to change the direction of maps. So I do another example of cheating here. I am going to use cochain complexes, but I'll preserve the direction of all arrows. If you want, you can say that I just invert the gradient of my chain complex, so that now all cells have negative dimensions, and then the directions will be preserved, by the differential will raise dimension by 1. So if you prefer, you can think about this in that way, but actually, I think, well, it is just a way of thinking about this. It doesn't depend, it doesn't affect the definition. So, if and only if there exists a collection of maps Mn from V to the 10th n power to V, every Mn changes the dimension by 2 minus n. It is precisely what we had here. Here we had to shift the dimension by k, but the tensor product was k plus 2. So actually, if this is n, then this is n minus 2, right? And if you take into account the change of dimensions, the change of directions, I have to go from n minus 2 to 2 minus n, right? That's because I'm going from chain complexes to cochain complexes. Okay? So Mn changes dimension by 2 minus n, and, which is more important, and now I'm almost sure I'm not able to write down all the signs, but I'll try my best to do this. So the signs, it is always the nightmarish thing here, the signs, but I'll try. And for every n, the following system of equations holds. The following equation holds. Sum And yeah, let's take A1 through AN elements in V, homogeneous elements. Homogeneous of dimension pi. So what we have here, we have sum over all p plus q equal to n plus 1, I think, right? MP, yeah, so forgot to say, sum over I from 1 to p minus q, n minus q plus 1, I think. Minus 1 to the power, I'm going to write this power a little bit later. It's something, okay. Okay, I try to write this power later, but let me begin with, we have MP, A1, AI minus 1, MQ, AI plus Q minus 1. Then you have AI plus Q to AN. Now the sign. The sign is that we have, I think it is something like P1 plus Pi minus 1 plus I minus 1. I'm not sure about this. This sign is almost a nightmare in this setting, remembering it and restoring it. I think I have never seen many papers in which these signs were correctly and accurately written down. All the authors prefer to use some abbreviation for the signs. Most of the authors prefer this, or just neglect them and write plus or minus. Even in Wikipedia. There they.
I think I have seen some books.
I think yeah, in Wikipedia they actually introduce signs, but they do a trick. They use they count the elements from right to left rather than from left to right. So yeah, I think the sign is correct. I checked it myself some few times, but it is something like that. So I'm sorry for this, but the signs are almost inevitably a nightmarish thing here. So these should be, oh, I forgot to say right-hand side. Definitely should be 0. So if you look at these equations, they're rather messy, but the first few of them are easily written down. The first equation is just up to the sign m1 of A is equal to 0. So M is just a cochain differential. You see, it squares to 0. And the dimension of M is 2 minus 1 is equal to 1. So it raises dimension by 1, right? It shifts dimension by 1. Also, that's the first. The second is a little bit trickier because here you have to use signs, and that's where all the trouble begins. I write it without signs, but yeah, it's something like this. M1 of M2 AB plus minus M2 M1 of A B minus plus or minus M2 A M1 of B is equal to 0. So these signs are messy because actually you should rather speak about the shifted by 1 space V rather than about the space V itself. You see? It is more correct. It is more correctly to speak about shifted space than about the space V. But still, we can write everything in terms of V, and you can see, and here you see that. So if you restore the signs to their proper places, and actually restoring the signs, you also have to restore the signs of M1, because when you shift the differential, cochain differentials changes sign. When you shift V by 1, the cochain differential changes sign. It's to plus or minus depending on the dimension of the element to which you apply it. Here, the binary operation also changes sign when you shift it, but it also changes the order. So if you restore the signs and the order of elements A and B, you will see that this second equation is precisely the condition that M2 defines a product in V, or in shifted V, with which verifies Leibniz rule with respect to this differential. Yeah. And finally, if you take a third thing, and you see that M1 of M3 A, B, C plus minus M3 M1 of A, B, C plus minus M3 A, M1 of B, C plus, and yeah, finally you have the third term of the same sort, M3 of A, B, M1 of C. It should be equal to M2 of M2 of A, B, C plus minus M2 of A, M2 of B, comma C. So this right-hand side is precisely the defect of the map M. We prevented it from being associative. So the left-hand side then is a cochain, right?
What does this expression mean? Mn change D by 2
So if you have a homogeneous element of which is just, yeah, precisely. So V, I explained that V is a graded vector space. Of course, I assume that you have heard about graded vector spaces, but actually, you can imagine that V is just kind of direct sum or direct product of subspaces, Vn. Sometimes you can even take it from Z, right? Then an element A is said to be homogeneous of degree k if A belongs to Vk. Right? The space V contains not only homogeneous elements. You can take some of the elements from different summands from this, right? But homogeneous of degree k is defined like that. Then a map F is said to be homogeneous of degree n so I mean F is from one graded space to another graded space. If F of A belongs to Wk plus n for any A in Vk. For all k, of course, and for all k. And for all k. That's what I call the space, the map shifts degrees by k. by n.
Градировку на тензорном произведении.
Oh yeah. So yeah. Sorry. I also have to take care of it. So when you have a tensor product of two graded spaces, then it's natural to introduce the gradient here by taking the direct sum of elements there can be some problem with finite and infinite dimensions in this case, so you have to be careful here. But in most cases, this is uniquely defined and there is no ambiguity. In order to avoid ambiguity, you can think that V has only positive gradings or only negative gradients, but sometimes you can avoid this. Yeah, but sometimes you can do this even without that assumption. Okay? Is this clear now?
Yes, thank you.
Okay, you're welcome. Okay, let's go on. So this is a definition of A infinity algebra. As you see, A infinity is just an extension of associative algebra. So in particular, every associative algebra is an example of A infinity algebra. But of course there exist examples which are not associative. And for our purpose, we need further development. So again, every associative algebra is A infinity. But we worked with Lie algebras rather than with associative algebras. So we have now to define high homotopy analogues of Lie algebras. They are called, there is such definition, and it is what they call the L Infinity Algebra. I'll try to sketch this definition first in terms of these maps, but then I'll give a kind of more or less invariant definition of these algebras. So, Lie Infinity Algebra, Lie Infinity. Higher homotopy Lie algebras, or L infinity algebras. So what do you have to change in this definition? So first of all, instead of taking a tensor product of V, you need to replace it by exterior products. But I'd rather even say shifted exterior products of V. So what is this? It is the tensor product, the nth tensor product of V by itself. But here you have to quotient out the relation of the following sort. A tensor B should be equal to B tensor A, but with certain sign. The sign should be given by -1 to the power A minus 1 times B minus 1 and minus in front of it. That's more or less what you do. Right? Mm-hmm. Yeah, A and B are, A and B here in top, they are just the gradients of A and B elements. Probably it would have been better to use these module signs to distinguish the elements and their gradings, but that will make my formulas much less readable. So I have to form this kind of graded exterior product of V. Then you have to, sorry?
So I don't understand the minus index of -1.
So here you have, so the index is -1 to the power module A, minus 1, module B. Sorry? What is module? It is module, so the grading of A is module A. I use this abbreviation. It is standard abbreviation in this science. Standard abbreviation in this theory. Yeah, they're homogeneous elements. Yeah, just like when you form the exterior product of usual vector space, you have to quotient out and B and BA. So you have to identify them up to the sign. Here you have to do the same thing, but the sign is dictated not just by the order of A and B, but also by their degrees, by their gradings.
So is it shifted?
Yeah, that's why I have minus 1 there.
So why I see.
Mm-hmm.
Why there is a extra minus 1?
Because, yeah, I mean, because it's dictated by, again, by the signs. If you, for instance, let us bivector pi, right? I have to reproduce the identity pi comma pi, right, equal to 0. So, and this should not be, must not be trivial, right? So that means that pi, 10 wedge pi, in this sense, should be equal to pi, I mean, not 0, yeah? So when I change the order, I need to restore the sign, the same sign. Okay? But pi, it has order 2. When I shift, it gets order 1. So if I remove this sign, I have minus 1 to the power 1. So the sign will be opposite. You see? But I need it. I need it the same. So that's more or less how I try. That's more or less how I remember the signs.
Not very natural.
Not at all natural. But yeah, you can go on in the same way. If you do it for vector fields, you should anti-commute, right? So they are x and y. X and y. Vector fields have degree 1. When you shift, they have degree 0. So if not for that sign, you would have get 0 here. So we would have minus. But we need to have minus. So they should anti-commute. That's why we put it here artificially, so to say. But if you think a bit about this, this sign is totally natural. The Koszul sign rule asks for this sign without minus whenever you just change the order of A and B. So when you take exterior algebra, you need to invert this Koszul sign rule, and that's why you have to add minus. You see? So that's totally natural if you think a little bit. But the way to remember this is a little bit tricky. Okay. Okay. So we have this. So we have to replace it like this. Then you also have a map L T from Ln from lambda twiddle n v to v. But if you try to restore the sign in that case, you're totally at a loss, because this sign will depend on the permutation you choose. So it is totally impossible to restore the sign, and that's why people usually write this equation just with plus minuses without any attempt to write the sign explicitly. And even in that case, even in this case, the equation look a little bit awkward, because you need to take the summation over all possible permutations as well. So now this equation looks like sum over p plus q equal to n plus 1. Sum over all permutations which are called unshuffles. Pq bar. So what is unshuffle. So the shuffle is a map. A shuffle is a permutation. Shuffle is a permutation which takes the first p elements, 1 through p, and the last q elements. And without changing the order of the elements in the first group, and without changing order of the elements in the second group, changes the order of the whole thing. Right? So if I had, actually I do have different colors here. So I'll try to draw it. So it's something like, you have elements 1, 2, if you can see they are blue. Have blue elements 1, 2, 3, 4. And you have, say, yellow elements 5, 6, 7. Then you need to preserve the order of blue elements. So you put 1 here, 2 here, 3 here, and 4 here. I need to preserve the order of yellow elements. So you put 5 here, 6 here, and 7 here. And so this is a typical shuffle. An unshuffle is a map which inverts the shuffle. So it actually restores these two elements from these. So that's what they call unshuffle. So you take the summation over all unshuffles. Now the sign, some sign which actually depends on the permutation of the unshuffle which you have chosen, and on the degrees of the elements that you use. Unshuffle, right. Unshuffle. So there's a definition for shuffle. Unshuffle is the inverse of a shuffle. An unshuffle is a map which is inverse to a shuffle. Yeah. I'm sorry, but that's more or less standard thing in this theory.
So shuffle is not a group?
Shuffles, no, they're not a group. They're just No, they're not a group, as far as I can understand. Maybe for some choices of P and Q, they are a group, but I'm not sure.
So for shuffle, you need all the elements of blue color to be just in front of all the
Yeah. Whenever it's like when in cards, when you shuffle cards, you just divide your deck into two parts, and then you put cards from the first part in between the cards of the second part, but you don't change the order of cards inside these parts. So if you imagine you just repeat this twice, you'll definitely get not a shuffle. So it is not a group, unfortunately. It's just a subset. So take this shuffle. Sorry? Unshuffle is inverse.
What is what?
Inverse of a shuffle, right. Sorry? Yeah. Well, you can try to find a combinatorial way to describe unshuffles, but really, I don't know how to do this in a short way, shortly. Maybe there is a way to do this. Okay, let's go on. So here I have L, P. But then you also have LQ. Now there is no need to put the operator M at some space, not in front, not in the very first space, because actually you can rearrange elements using the permutations. I'm sorry. I'll call my mom later. Here you have A sigma of 1, A sigma of Q. Or maybe you need to exchange the order Q and P here to make it. Maybe it's better to look like this because P is in front of Q more or less, right? And then you have the remaining part. I'm not going to write this down. So this should be equal to 0. This is the definition of L Infinity Algebra, or strong homotopy Lie algebra. Again, this algebra encodes all the higher homotopies which you might need. So it's equal to 0. I wrote this, but let me repeat this here. So how much time do we have? Let's speak about, let's say about 15 minutes. So the first few equations of this sort are readily understood again. And the first equation is just, again, that L1 squares to 0 up to the sign shift, right? So it gives you a cochain differential again. Then you also have the equation that L1, L2 gives a map from lambda 2 V into V. And L1 verifies Leibniz rule. With respect to L2. So that's first, that's second. And the third is that, so what is an analog of associativity in case of Lie algebras? It is Jacobi identity. So it is much harder to see through all the signs here, but it is kind of well-known fact that L3 gives cochain homotopy for the Jacobi identity, for L2. So again, every Lie algebra is, as they say in French, par excellence, L Infinity algebra. If you just put all maps Lk beginning with L3 equal to 0. L1 will just be the differential, and L2 will be the bracket. Yeah. So if you do this, you'll get the infinity. But actually, there exist many examples where you obtain genuine L Infinity algebras. For our purposes, we shall need maps of L Infinity algebras. And it is also possible to write down maps of L Infinity algebras in terms of, well, what they call Taylor elements, Taylor coefficients of this map. However, trying to do this will bring us quite a messy equation, which will be hard to understand unless you are familiar with the definition, with the invariant definition of L Infinity algebra. So now I'm going to give an invariant definition of L Infinity algebra, and that will give us a possibility to introduce maps, morphisms of L Infinity algebras in a very short and accurate way. So invariant definition, that is a definition which doesn't involve these Taylor coefficients L1, L2, and Lk. All these Taylor elements, Taylor coefficients, will be put together into a single object, so that we shall speak about this object as a unique object in the future. So another definition. So the first part of this definition is the following. Consider the exterior power of a shifted V. The shift, as I explained, I think I can already explain this, but shift is again a graded space. But this case, Vn is equal to Vn plus 1. So we shift it by 1 to the left, so to say, or to the right. It depends on your, your point of view, what is left and what is right, right? So we shift it by 1, and it only amounts to the fact to change in the gradients, and that's all. Now you can form exterior powers of this shifted vector space as just as usual, without this extra minus sign which I used here. So lambda n of W is equal to tensor power nth tensor power of W, where your quotient outer relation A tensor B is equal to minus 1 to the power A times B, B tensor A. So I hope I'm not I'm not making a mistake with the degrees, with the signs. At least the signs, yeah, probably minus. Yeah, now it's correct, right? It's precisely what I did before. Okay. Yeah, but here I use this usual gradient because I already shifted. Right? You see, since I have already shifted, I use the usual exterior power of graded algebra, of a graded space. Okay? So this is the definition of lambda n. If we take the sum of all lambda n's for n greater or equal to 0, we obtain what we call lambda dot of V. And for this, this space is very important space for us because we can endow it with some algebraic structure, quite simple and very combinatoric in its nature, but very important for us. There is a map delta from lambda dot V, V1, lambda dot V1 to the tensor product lambda dot V1 tensored with lambda dot V1. This map is given by the evident formula again. Delta of V1 Vn should be equal to the sum of all unshuffles of minus 1 to the sum power epsilon V sigma of 1 V sigma of P and sum over sum over all P and Q, of course. So here we have wedge V sigma of P plus 1 wedge V sigma of n. So you see this formula is pretty trivial. We just reinterpret one of the elements in our tensor product as being exterior with respect to the remaining part. Right? So it's just kind of tautological coproduct. But this coproduct is actually very important because it is universal in some sense. So first of all, this tensor product, this coproduct, coproduct is co-associative. That is to say, delta tensor 1 delta is equal to 1 tensor delta delta. That's easy to see. But also, delta is co-commutative. When you change the order of elements, this and this element, take a twist, and you obtain the same map here. Of course, you have to change the order using the sign convention, right? So T is a swap, sign swap, swap. And this gives you the graded. Sorry? T is a swap, the map which changes the order of tensor legs. But using the sign convention. So you take care of the sign when you swap it, right? In this sense, you can say that lambda of V1 is a co-commutative coalgebra. Co-generated. I don't like this co, but it is standard thing in this theory. Co-generated by V, shifted V. But what is the universality of this algebra? It turns out that this algebra is actually co-free. So you all know probably what is a free algebra. Free algebra. Yeah.
Там все лучше во всех определениях ставить скобки, потому что shift на единицу может означать shift пространства перемены.
Oh yeah. Right. Yeah, but it will make our make the whole business much more lengthy, much lengthy. Yeah, right. But when you are used to this, you usually understand where to put the brackets. Yeah, it's kind of for the person who is just in beginning, who is just initiating, kind of initiated into this. It's better to keep trace of these brackets here, parentheses here. Okay, what is free algebra? Free algebra generated by V, by a vector space V. It is an algebra such that for every map, so V is inside this algebra, right? V is included into this algebra. And for every linear map from V into an algebra A, for every algebra A and for every linear map, there should exist a homomorphism from this algebra to this algebra, which would extend this from V to the whole algebra. So if you want to get the definition of co-free coalgebra co-generated by V, you should invert the arrows in this diagram. So CV is a co-free coalgebra co-generated by V if there is a map from CV into V, canonical projection, and such that for every coalgebra C, such that there exists a map from C into V, a linear map, there should exist a homomorphism of coalgebras such that this diagram is now commutative. As you see, first of all, it comes with some as a kind of, it is very natural on one hand. You can give this definition automatically from the definition of free algebra, just by inverting all the arrows. But on the other hand, it comes with a surprise. Here you have a map not from V into C, but from C into V. It turns out they can extend a map not from V, but map into V. So please try to work out this definition a little bit and see for yourself why this space is in fact a co-free coalgebra, a co-free co-commutative coalgebra. I'm sorry, I need to add the condition of co-commutativity here to make it work properly. If you just want to get a co-free coalgebra, then you need to take the tensor product, the tensor algebra of shifted V, again in parentheses. Okay? So the tensor is just co-free coalgebra. So you try to work with co-free coalgebra first before you work with co-commutative co-free coalgebra. Okay? And then check that a similar map in tensor algebra defines the structure of coalgebra in it, and that this coalgebra is actually co-free in that sense. Now, the definition of L infinity algebra is very simple. So definition number 2, which will be probably the last definition today, the alternative definition of L infinity algebra. V is L infinity algebra if there is a map L from this co-free coalgebra, co-generated, co-free, co-commutative coalgebra, co-generated by the shifted V. I'm sorry, but there are too many codes here, but I don't know how to avoid this. Into itself, which is first, it is homogeneous of degree 1, and second, it is a homomorphism of coalgebra, a co-derivation of coalgebras. So what is co-derivation? It should verify a co-Leibniz rule, maybe. Let's go like this. So L tensor 1 plus 1 tensor L applied to delta of A is equal to delta of L of A. Now, it is a good exercise for you to check that since our coalgebra is co-free, then this map, this co-derivation, is also uniquely determined by a map from coalgebra to the space of co-generators. And in this way, you will restore the Taylor coefficients L1, L2, and so on. I think this is a good time to stop here now. Next time, I'll begin with this place, and I speak about L infinity homomorphisms and show how they lead to how they define the transfer of Maurer-Cartan elements. And I'll explain, formulate and probably sketch the proof, a start sketch in the proof of Kontsevich theorem.
So finally, which kind of algebra will you use? Infinity or L infinity?
L infinity. But A infinity is simpler. All formulas in A infinity are simpler. A infinity was given just because it is, when you start to learn something for the first time, you should begin with a simpler version of the notion which you are going to learn. It's like you never start learning multiplication table with multiplication by 13, for instance. You start learning it with multiplication by 2, right? Something like that. You start learning mathematics when you start with operations on natural numbers. And then you pass to negative, to integers, to rationals, to real numbers, and so on and so forth. So, okay, are there any questions? Any further questions for today's talk? Yeah. So coalgebra, okay, nice question. Coalgebra, again, you know what is algebra, right? Draw all the diagrams would define algebra. So what is algebra? You have a map like here, yeah? Then you also have a map from the numbers into A, which is the unit, right? And then you have several conditions. For instance, you have associativity condition. A tensor A tensor A. You can first have this M tensor 1. Then you can the same M, get here. But you can also begin with 1 tensor M, get in A tensor A, take M, and voila, you have the associativity condition. Okay, you also have unity condition, that the map that this is unit. Right, what is unity? It is this. You have a map A. You have the space A. You can identify it with A tensor C over C, right? Then you have a map from here to A tensor A, 1 tensor epsilon, right? And we have product. So this should be identical. And also when you put it on the left. Right? Now if you want to give the definition of coalgebra,
Yes.
invert all the arrows.
Yes, but the tensor is over C.
Yeah, over C. Sure. Yeah, just I prefer C because I'm not algebraist. I'm not that algebraist, as much algebraist as others.
Because many effects appears only on
Yeah.
Q.
Sure, sometimes it is important to work over Q, right? But you will never convince me that it's important to work over finite characteristic fields. Yeah, probably it's important for algebra, for some algebraic reasons. Yeah, even in topology it's sometimes important. That's right. But it is much harder for me to understand that. And actually this definition works over an arbitrary field. So now if you want to get the definition of coalgebra, invert all the arrows. And you'll get first a map from C to A, which is called coproduct. So C to C tensor C. And you get a map from C into the numbers, which is called co-unit. And then you get a co-associativity condition and also the co-unit condition.
You can give a typical example.
Well, typical example, I think I'll give you a typical example, this co-free coalgebra. Yeah.
I mean, those example which is familiar to everybody.
I mean, you mean the group algebra?
Something like that.
Okay. Okay, let's speak about this next time because it's already 8:30. It's too late. Okay? If you want, we can discuss this example next time, but we can also discuss them with you in private. Okay? So, okay, I think it's time for us to stop here anytime. Okay.
Any questions?
I think no.
There are 3 more students actually.
3 more.
Eric Shen, Vlad Musov, and Yasushi.
Yasushi.
So if there are no more questions, then bye.
Okay. Bye.
Next time you can come to here.
Yeah, I hope next time there will be no problem, no political reasons to stay home. I hope by next time.
And also no national
Holidays. Right.
We
8th.
will be in Novosibirsk.
You will be in Novosibirsk next time. I will be I will go there on Wednesday.
Really?
Yeah.
Okay, then I will not be here.
You will not be here. Okay, but you can join us by.
Okay.
It will be too late for you.
Yes. Well, if I can, then I will.
Yeah. Okay. So yeah. Okay. See you next time. Bye.